Right, so I think one thing I should add in the morning is I will need to assume, oops, I see, G, oops, where's black?
Your first click this one. This one, yeah.
Oh, I see, I see. Okay, because G need to be, let's say, unramified. It's supposed to also work in the Tame ramified situation, but things hasn't been checked carefully, and there's also, yeah, this is one thing I want to say. The other is actually the maybe I should also say is this part of thing will also work. Okay. Okay. I hope this is okay. Maybe. All right. Okay. Yeah, yeah. The other is some. Oh, let's see. Wait. Why? Why I always? I thought it was okay when I was testing. Maybe this is actually. Let's say, to prime, I actually need to really discuss is some T exactness of maybe I borrowed the notation this morning of like SIP psi Tame. This is something I want to also discuss. It's gonna be. I think that's right. It's gonna be this some analog from the automorphic side to the quasi-coherent sheet. Okay. There's some T structure on both sides, and something I want to discuss. So some two things to add. All right. Okay. So where are we? So in the morning, I was talking about this theorem, like some structure of this category, automorphic category shifts on ISOC, G, and I haven't really talked about the proof, but it sort of gave you some idea of what is sort of recall what is the shifts really mean and how to kind of work with it. At least give you some idea. One can work with such kind of abstract concept definition. And then I talked to some special case when there's categories compactly generated, like when the situation is when X mod H, this category shifts is compactly generated, and also it's dualized, it admits some self-duality. So let me just start by try to illustrate how to get the proof of first and second fact. Maybe like this third, like a accession or whatever, a semi-orthogonal decomposition. It's really, once you have this adjoint functors kind of formally follow from. Actually, first three parts are kind of all kind of formal. Most. But I think it's also because to give some idea of proof, part one, part two, it's also a good time to introduce how some auxiliary object we need to understand the shifts in ISOC. This actually was already introduced, I don't know why. Maybe I should facing this side. Main two. To understand this, because this is a kind of very complicated geometrical object. It's kind of a quotient of infinite dimensional group by some infinite dimensional group. So, and this infinite is really infinite. So is by the so-called, I think this local Stuka for this map. I don't know, maybe some et al. Version, where P is some parahoric. And actually, most time will be just Iwahori. For most discussions. It's only occasionally, maybe at one point we need more general parahoric. And the whole point is, and this Stuka is basically very similar to the definition of isocrystal. Now it's E is just the p bundle. Because P is parahoric group scheme, so it's defined over O. It's a random integer, so it's p bundle on the whole disk. And psi is an isomorphism of this, and it's Frobenius pullback. But you only isomorphism over the puncture disk. Okay, so this you can write it as Lg modulo the Frobenius conjugation by L plus of P. So L plus P is a positive loop group, usually called. So its functor point is L plus P of R. It's just the P of WO of R. Okay. So this is a kind of this infinite dimensional group, A, like this H we used in the morning. So it's, I mean, we mentioned it's a pro-algebraic group, but it's a pro-unipotent radical. It's codimensional, finite codimensional. So quotient is actually a finite dimensional reductive group, like a quotient. So, and then this map was already mentioned is improper. Maybe finite presented. So if you look at the point downstairs, the fiber, if you have any point for any B, the fiber is basically isomorphic to so-called the affine flag variety, some kind of partial affine flag variety for any, let's say, B inside here. If you to work, so it's kind of an improper variety. If you want to work over families, general spec R point is slightly subtle, but yeah, it's something like that. So using this, so this actually tells us then you can do the whole check nerve. Then just so I'll write this. It's kind of the I write the heck. I mean, it's kind of some heck correspondence. But you can also just define. It just defines you have a map. You can take as a check nerve. So what does this classifies? I will not write it, but let me just say what this classifies. It's basically two pairs, a pair of p bundles, and then. There will be some psi Frobenius pullback of one is isomorphic to another on the puncture disk, and also isomorphism of these two p bundles on the puncture disk, compatible with this Frobenius pullback. So it's kind of some kind of like heck correspondence. So that's the reason, right? This and everything. So because this, then using this improper descent, you see that maybe that's the reason. Shifts on ISOC actually is a co-limit. I come to the co-limit of all shifts on each of this. Maybe at the DAW means I really recall this check nerve. And so we just play the game as before to prove shifts on ISOC to this category is compact generated. That means canonical duality. I just need to prove each term in the check nerve is compactly generated. There's some self-duality and compatible with all the transition methods. Okay, so that's the idea. But then each term is actually pretty concrete. Let's just do the follow. Yeah, let's just do the first term. So the Stuka local P itself is actually itself is also co-limit now of I write the SG P modulo the conjugation by Frobenius conjugation by L plus P. What is this LG less than equal to W? This actually was somehow mentioned at the end of the end of the last question someone asked, and I answered this. It's kind of because you have this where this L plus G sits inside the LG. Let's go to the this partial flag right here. You can take some shoot. So let's call this is a flag, and then here you can take some Schubert variety inside it. This is really a finite dimensional variety, maybe singular, but it's kind of projective. Then you just take the fiber product. So then this is like a standard plus it. Yes. Okay, and then shifts on LG more sigma L plus I. Again, it's going to be the co-limit of all this. And actually, we already mentioned that here, right? This guy. Now we are exactly in this situation, and each one is compactly generated with some nice duality. So, of course, this involves some choice, but you can carefully make such choice, make all this compatible. That shows this. That implies this guy, like this one, is also compactly generated at the mid-duality, and then also you have this co-limit presentation. And then it's not just for this first term of check complex, but every term of check complex you can write similar way. So you get this one is compact generated and the mid-duality. Okay, so this is kind of formal. So that's kind of the give a sketch of basic idea of first part of this two theorem. Maybe I'll skip because of time. I'll skip the other parts. Part 4 is kind of more or less discussed in Minja's talk, so maybe it's fine. The part 5 is a little bit more subtle, but ignore that. Okay. Any questions? Okay, so now no question. Now I want to start really the what I'm trying to say the second lecture this afternoon talk. This which contains really some content and some like non-trivial input rather than. So the second part is next goal is sort of define. To define the Tame part of this. Okay. So I would really just define as the following theorem. It's kind of give a. So let me state it as a theorem. So the following subcategories, full subcategories. Of shifts on I sub G are the same. What are the three full subcategories? The first one is those F such that its restriction, strict restriction of G to each strata, so is so because of previous theorems, when I restrict a shift to a strata, this category shift on a strata is just a category smooth representation of the corresponding group J. You can think about this is a representation inside here. Of course, derived category, but I want this is to be a Tame representation, meaning you people all call depth zero representation, meaning so this is a depth zero representations blocks. So it's this was probably already mentioned last week, or no. So let me okay. Let me finish the stated theorem and then recall this. Second part is F. So you take upper star restriction to each strata. It's a Tame. And the third is the subcategory. Generated under colimits by what I write as object of this lower star delta upper shriek of F. You write E, where we have. Let me write on this diagram L G ma I plus where we write in the next where comes the L G ma I plus ma Frobenius conjugation of T. This is kind of this horizontal transform. The whose finite dimensional version I think appeared in last week in Arnold's talk. So this so T is really T. So I'll where let me so I need to bunch of notations that I haven't. So where I is a L plus of I, so it's a you are Hori. I plus is a pro-unipotent radical. And maybe I should write this T as a T over K. Maybe, I don't know if it's better or not. So then T is I ma I plus, which is a finite dimension torus. So in the case of the group is unramified under assumption, you also have some, let's say, maximum torus in a Borel, which is unramified torus. It has a natural extension to it has a natural extension to a torus over O, and you just take its spatial fiber. Yeah. So that's TK is this. Okay. Oops. Sorry. And then finally, E is a monodromic shift on Yeah, actually, maybe I don't really, here I even don't need to take the quotient. So it's just to take a monodromic sheaf. T monodromic sheaf plus. As far as I understand, there was some discussion about this, because once you have a torus act on some space, the notion of monodromic sheaves makes sense. So basically, those sheaves really are Tame locals for each torus orbit. The sheaves are kind of a Tame local system on every torus orbit.
The action given by this conjugated adjoint act, or
I mean, the T monodromic is there's a T act from the left and a T act from the right. So maybe I should say T bimonodromic, but it's the same as one side monodromic, I think. Bimonodromic. So yeah, so there's action of T from the left and also from the right.
So assuming the correspondence in the middle, maybe I plus?
I plus, yeah, so plus, yeah. So I must did something wrong when I hold the pencil. So. Okay, here is I plus. Okay. All right. So that's a part of the delta is this map. This map, or maybe delta plus if you wanna just do delta plus. Let's just write delta. Okay. So and then once you have the theorem. This is theorem I will discuss today. It's kind of, and then the definition is, Tame is the full subcategory described by this as in the above theorem. Okay, so that gives a definition of. And actually, this is actually holds not just for this is for any coefficient, not just QL coefficient. FL coefficient is also okay. CL coefficient. Any question about the statement of the theorem?
can you add more items? Like, is it also generated by IV lower star of Tame stuff under colimits?
It's also generated by
You don't have to write it.
Yeah, it is because of this accession or whatever. Once you have 1 and 2, it will be. Yeah, it's also can be written as it's generated on the colimit of IB lower star of a depth 0 representation, or generated by those IB lower shrink of depth 0 representations. Yeah. Okay. Right. So let's schedule proof. So the goal is to schedule. But maybe before sketching the proof of the theorem, I want to first see something. There's something subtle in the proof is the following. So let's first analyze what. Let's even do a simpler version is to replace I plus by I. It's called the unipotent version. But let's first analyze what do you get under this correspondence. This was in a finite dimensional situation. Actually, this was described, analyzed by Arnold. But let me try to see a little bit. So now I have this Stuka, the map to this. Then let me okay. Let's just do I version. So if I take some E to be, so inside here I have a usual like Schubert-Broha stratification. So for this, let's fix some W. W now is in the F and Y group. It's extended F and Y group. Then let me call this is IW. So if you take E to be the star extension of, let's say, some constant shift or dual length shift, some lambda, maybe up to some shift, I take this delta, and then you can try to compute what you get. And if I take some B, let's see, some B here, okay? We already see the B fiber here is kind of isomorphic to, if you do not take some W, but just look at the fiber over B, this is look like this LG mod I, sits inside here, mapped to here. Maybe it's not, shouldn't write in belongs to, it's really a map because it's stacky, so I really take a point here. So if I take a map, a point here, the fiber is this L, is this FN flag variety, but I'm pulling back of the shift not on the whole L double cosine LG mod I. I'm pulling back a shift only supported on here, on Schubert cell. So what you get, if you just look at the fiber, this inverse intersect with delta inverse of a Schubert cell. This is has a name usually called the so-called the affine Danlustig variety. Okay, and this was originally introduced by Rappaport, study reduction of Shimura varieties. It's kind of very much like the analog of the Danlustig variety in the finite dimensional situation, except in the affine case, there's the usual, like the Danlustig variety in the finite dimensional situation is just there's only one parameter, W. For each W, you have variety. Now you have two parameters. One is W, one is B. Okay, so there's two, and then on it there's this action of this GBF acton here. This, like because this GBF act on B, so act on this variety. So then this induction, let's see. Yeah, maybe I should do this. Oops. Over here. Then what this, it turns out is if you do, yes, so, sorry. If you do upper shriek of this E and the north star, and then restrict to this point, B upper shriek. So what you get is really just the, what you're computing is exactly the homology of, or cohomology of this affine Danlustig variety. Maybe up to some shifts. And this is what is the representation you get? You get this representation of JBF. Okay? And so some remark, which is which I want to see, which makes this theorem a little bit subtle, is a remark. This has breaks up as a union of irreducible components. The irreducible component actually is pretty complicated for general W and B. We don't really understand There is some understanding of how this works, but we don't understand in general. And each irreducible component will be acted by some open compact subgroup. Some open compact. I mean, the whole periodic group JBF acts on the whole affine linguistic variety. Each irreducible component will be actually fixed by some open compact subgroup. So there's some, let's say C. So the stabilizer C is there's some open compact subgroup. So this is some open compact. And of course, this is each irreducible component. This is a finite dimensional variety. This is kind of a known result. The even general dimension formula is not clear, but we know it's finite dimensional. Then this open compact act will factor through some quotient, finite dimensional quotient act. Let's say bar. However, fact is this K bar may not be the finite group of Lie type. So, in other words, this action doesn't actually what acts on each irreducible component of the linguistic variety actually could. There are example, for example, in the unitary case, the group what acts on some irreducible component is not the U of FP, but the U of FP squared or U of FP cubed. So a priori, if you compute its cohomology, a priori you might be see higher depth representation appears, because it's really geometrically some higher. It's not the geometric action is compact. Open compact does not act through the finite reductive quotient. So. U Z mod P square or something like that. There's this kind of, there are examples. Yeah, it doesn't really factor through finite dimensional quotient. So, okay, so that's the remark I want to make. So it's a priori not obvious that everything, if you just look at the geometric, how the fiber like this, the cohomology may appear higher depth representation. Kind of, it looks like an induction from some smaller open compact maybe. But it turns out what you get is you don't get anything higher depths. So then, but the proof is actually proof is now sketch proof. So the first step is this so-called the linguistic reduction method. So it turns out in order to study what kind of representation you can obtain from this induction, this usually horizontal transform, you don't need to study arbitrary W. Arbitrary W it's in general a really complicated thing, but it turns out that you only need to study some particular one. So this is so let's suppose you have if you have some W and some in W and some S is some simple reflection in the FML group. And maybe okay. Such that the following holds: if you conjugate S, W, and the Frobenius act on the group, so it also induces the action on the FML group. I mean, if you choose this, all the Borels, these are like Frobenius stable rational ones. So it act on. So such that if the length of this. Okay, so F and Y group is quasi-cluster group. There's a natural length function. And if you conjugate, if this length dropped by 2, maybe, or add length, add by 2, let's write the, or maybe, I mean, depends on. Huh?
Do you want to put sigma S inverse?
Simple reflection, so S and S inverse are the same. Yes. Right. So maybe psychologically, maybe less than 2. So then we can look at what happens is you can look at the following thing. You can look at this. Okay, this look at W. This is defined to be L W modulo just a Frobenius conjugation by I. Let's write in this map to Isaac. So if you think about it, if we come back to here, if we understand the oops, what is it? If we just do the oh, by the way, we can to study what the category what generated by this of this OE. If you just look at here, this category, because of the stratification of this double closed by Schubert cell, it's to see what category you get by this kind of horizontal transform or what's called the F-and-Lustig induction. It is enough to just consider this kind of objects, what you get. Okay, it's if you want to see what category, what kind of shifts on Isaac you get, it's enough just the category generated. You just need to generate by this, and if you think about it, that's exactly what happens is then this delta upper shriek of this E, maybe called EW. Actually, I think it was already introduced in previous talk called the co-standard object, so I'll maybe just use it. I just realized this must be already introduced. So this N. Then this is basically just, if I write this, it's just the push forward of the constant shift on, or maybe dualizing shift. There's some kind of different on this up to some shifts or something. Maybe dualizing shift. Let's make it more correct. Write it more correctly. It's dualizing shift. Okay, so basically, recall what we are computing is what kind of thing we get under this map. What can we get? Understand this shift is push forward. Here I haven't talked about this this condition, why this length function is useful, but now notice that because of the multiplication by this Bruhat, I mean, this usual BM pair business, how to multiply in two I double coset, you will see this guy itself can be written as the following thing, Stuka. I'll take some, maybe not this one, but write more carefully. So write as LGS times I times LGS W sigma S times I of LG sigma S, then modulo Frobenius conjugation by I. Okay, this comes from this length function at once you have this length function W1 plus W2, the length of W1 plus W2 is the same as the length of W1 times W2 is equal to the length of W1 plus the length of W2. then the double coset multiplying, so you get this. And then there's this, all this geometric incarnation of this trace business, or this originally, like this, or this, actually essential point of all this Stuka stuff is the so-called the partial Frobenius map, which you can move this to the left-hand side. So this is going to be isomorphic to this one. So this is a so-called the partial Frobenius. It's kind of, if you think you can interpret this as like using some modular interpretation, you can interpret this as some bundle E1, it's Frobenius pullback, Iwahori bundle on the disk. E1 go to E2, go to E3, then go back to E1, such that it has some certain relative position. Let me write this as, for example, let me write this as W prime. So it has this kind of relative position. This is going to be S, W prime, sigma S, something like that. Then what the partial Frobenius does is you can apply the whole Frobenius endomorphism of this factor. So then you will get E3, W prime, E2, sigma inverse W E1, and then sigma E3. So this is now W prime, so this is sigma S, and the relative position sigma S. So that's this is what you get, this isomorphism tells you. So this is some kind of you write first, because of length or this length add, you can write the modification of bundles as an iterated modification and apply the Frobenius just with one modification. So this is a crucial structure appearing inside the story. And but now there's this fact is if you just do the convolution, this will map to LG. Now I have two simple reflections. If you convolve them, I multiply two double coset, you will land, turns out land in this, not just one double coset, but the union of two double cosets. This simple reflection and the trivial double coset. This is, again, this is a usual BM pairs arc type thing. And you can look at, so therefore I can factorize this push forward. See, what I'm trying to do is maybe let me write it, give it a little bit further. So what is I'm trying to do is this will actually map to less than equal to here. Okay, so what I'm saying is this push forward I'm starting, then the shift I'm starting is I factorize as using this sequence of isomorphism, then push forward to then this push forward to iso. And what we use is this is come from here. Gives this. Okay, so maybe. All right, but the point is the space is doing this, but the whole point is when you do the push forward, if I model I just from the left-hand side, it turns out that what happens is you can, because we are pushed forward constant shift, so I want to also understand how the constant shift are pushed forward on this map. So it turns out that this constant shift, if this is denoted as pi, then pi lower star of the constant shift, I left-hand side modular I to make everything finite dimensional, will be, actually there will be, turns out the fiber sequence, I can't remember which is which, but it's roughly speaking, it's just a constant shift supported on I mod I up to some shift. Then another one is just this constant shift support on LG sigma S, the mod I. Okay, so actually it's not a really direct sum, but it's I mean, it's actually a fiber sequence. There's a, I can't remember which one is, you know. I mean, this push forward sits in the middle. It's going to be extension of these two shifts. One is just this constant shift support on this unit coset. Another is this constant shift support on this non-trivial Schubert cell. And it's kind of, there's some, maybe there's some, yeah, there's some shift and also some multiple. But it's basically something structured like this. So therefore, you will see that the conclusion is, if you notice this, is then the push forward. This is really the key thing. The push forward of this upper shriek of this object itself will be contained in the category generated by two things which are similar to each other. One is just push forward of so delta W prime, because here I have this constant one. Then I further multiplying this one, I will get just W prime. Okay, so this is my W prime. And the other is I put some S, so I will get N star per shriek of W S prime S. Okay, so if you just wonder how this category, which subcategory generated under this procedure, you can replace W by W prime and W prime times S. If there's this length combinatoric condition of the length function. But this is good because now you can iterate the general W is very complicated, but if you are only carrying what kind of shifts you get on the ISOC after up to the category generated, I can iterate this step because the length is every length is finite, right? So I can always make it at the end reduce to the case that so therefore this implies the whole category generated by this this is E. This E is the same as just those generated by W for W minimal length in its sigma conjugates class in W tilde, the F and Y group. Oh yeah, by the way, there's some non-trivial fact involving here is if an element is not in the minimal length, you can always find some S after conjugation to make its length drop. So this is a non-trivial fact actually proved by using some combinatoric input. Some combinatoric input by, I think this is Sanye and Xu Hua He. I mean, if the whole point is if W is not minimum length, you can always do this conjugate, find some simple reflection to reduce the length at least by 2 and by 1. So you get this. Now the minimum length ones are much easier to, I mean, the affine Springer, affine Dennloustig variety I mentioned here, it's kind of, for general W, it's very complicated, and this, for example, the open compact act on it may not, does not factor through reductive quotient. But for minimum length one, there's a much nicer thing. And this, for that, I also need to explain another situation. Is, yeah. So this is a situation I explained when the length, if you conjugate by some s, the length drop by 2, you get this. But if the length does not drop, actually, it's also quite interesting. If, so SW, sigma S, this is W prime, equal to W, and if, not equal, sorry, if the length equal, and the length of now I get I need to figure out length of W equal to the length of SW plus 1. So then you can do the you can do the similar thing. It will be like I can write as LG SW delta sigma S Frobenius conjugation by sigma I. But now I do the inverse of partial Frobenius. I think I will get now I get sorry. I guess I get a little bit confused. I want to, maybe I, right. I could write it in this way, sorry. I think this is what I need. I write this as SW. Okay, that's the correct thing, because S times SW is W, but the length at. So then this one will be isomorphic to, again, apply the partial Frobenius. Sigma S. So this will be just the same as, look at W prime. So in other words, if you take this conjugation by this S, if the length doesn't change, then you get basically the same variety, and the image, you will generate the same sheaf. Okay, so therefore, and then using, again, some combinatorics, of F and Y group. So we can assume that so then the category is, we just need to understand the following thing. W where W is of the form so-called right X where this is some kind of combinatorics where let me just how to write the U K C contain X is an admissible triple. So then I need to give you the definition of an admissible triple. Which probably triple consists of U is the so-called it's the element in the F and Y group, but it satisfies very strong particular combinatoric properties such that the length of U times length sigma U times the length of sigma square of U, blah, 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 times the length of, let's say, N sigma U, maybe N minus 1, is N times the length of U for any N. Such element actually is called a strict element in the F and Y group. Some particular element, for example, translation elements are always like this. K is a subset, the subset of simple reflections or in W tilde such that the following two conditions holds. First of all, the Y group generated by such WK is finite. And also, I want to, let me just try to write this correct. Just give me 1 second. X sigma WK, oops, sorry, not X. Now I've realized the problem is in my notation, in my notes I use this another notation, this XU. Sorry, U is so first one, like up to conjugation by X sigma conjugate, X sigma WK, X inverse is WK, so this is sort of invariant under certain conjugation. And also X is minimal length. In the double coset. And C is an elliptic AD6 sigma conjugate class of WK. So because of this condition, this makes sense. So you do have this conjugation on WK. So there's some non-trivial combinatorics, pretty non-trivial combinatorics to see that because of step 2, to study what kind of shifts on ISOC you can obtain by this F-analytic reduction or horizontal transform. You just need to study those W of this form, and then satisfying certain condition. And here is this, you see this finite W appears, and then the last result, I want to, sorry, I have maybe 2 minutes to finish, is the theorem is, it turns out if you just want to study what this guy of this particular form is XU, so this guy, it turns out the same as it's literally isomorphic to this sigma, but this X sigma, this twisted conjugation by so how should I say that? Okay, I need to maybe introduce one more notation. Yeah, so, yeah, sorry, let me just introduce one more notation. So, given this XU, maybe this quadruple, maybe. You actually get the, let's see, W is an element in the F and Y group. You can lift it in a group, so you get this B. This B is this, let's see, let me just write as X, some lifting of X into the p-adic group. This gives you, and then you get G of B, and this will actually, you get also the Iwahori inside here, G of B. There's some way to get standard Iwahori. And actually what happens is this Stuka theorem, in this case, you can understand this space very explicitly. This will be just, if I, okay, right, maybe. Actually, it's just this, you can consider the finite dimensional Dunlustic variety associated to U, the modulo G of BF. So what is this, or maybe not, XU, where XU is the classical Dunlustic variety associated to U inside this WK, and such thing actually will give you some, which can be realized. This is which is the Weil group of LK, which is where LK is some finite dimensional reductive group determined by this. You know, I have this F and Y group. I have this finite subset of simple reflections. So that actually determines a levy of a parahoric. So where is this is a levy of the parahoric associated to some kind of standard parahoric associated to K. And then this Frobenius structure is given by the not usual Frobenius structure, but you need to sort of twist the Frobenius structure by X. So at the end, this particular, the general, you know, the local Shituka or like F and Dunlustic variety is very complicated. But at the end, for this particular case, it's really reduced to the, you know, this kind of, sorry, it's not the modulo this. It's this modulo I, the Iwahori. Yeah, I think. Or maybe some parahoric. Yeah, sorry, this is a parahoric. Get some P of K of some O points or something like that. Yeah, but this O points come from this twisted Frobenius. Yeah. So yeah, at the end you see for this kind of thing, it becomes just a compact induction from some Danilistic varieties. And the other part of theorem is to actually show exactly. And then we use this result, Danilistic in a finite situation, or maybe for modular coefficient, maybe Bonafé-Rouquier, that all the representation of finite group in D type can be obtained by Danilistic induction to conclude. Okay, so I think I stop here.